Hi everyone, welcome back to the AI language. So this is going to be pretty exciting because till now we have been working with MCP servers that have been running locally on our computer. And as you can see in this particular infographic, that is what the general trend has been even with Claude Desktop as a client and Python or JavaScript servers which run on our computer. Now we have a chance to use server sent events and build a MCP server which basically connects through an HTTP connection. Before we begin, let me show you a quick preview of how I used an MCP server and deployed it to Google's cloud to get a URL for the service and then use that URL to start my MCP client and connect to the server and invoke tools on the server using Gemini's large language model. Alright, so once the push command is completed, we'll actually run the deploy command. This is gcloud run deploy. We provide the name, which is MCP SSE server. Then we provide the image tag. We basically use the managed platform. We choose a region and we provide a port and we allow unauthenticated access for this demo. Let's press enter to deploy it. Alright, so this deploys and provides us a URL for the service. Now let's clear this and move to our client directory. Now we'll write uv run and then we'll write the name of our client and we'll provide the URL that we just got and we'll put SSE as the endpoint because that's needed for initialization. Now let's press enter. And guys, is this not amazing that now we have our MCP server running on Google's cloud over here and we are able to run our client with that particular endpoint. So now we get initialized SSE client listing tools and is connected to server with tools run command and add numbers. MCP client has been started, type quit to exit. So let's type our query. So we are going to use the add numbers tool and I'm going to ask it to add two numbers. Now I've asked it to add 2 and 4 using the add numbers tool. Since it's an easy operation, I specifically mentioned the tool to be used because I want Gemini to use the tool rather than just adding the numbers itself. And now we'll check whether our MCP server hosted on the cloud can actually connect with the client that's running on our laptop right now. Let's press enter and see what happens. Okay, so Gemini requested tool call add numbers with arguments 4 and 2. That's perfect. And then the sum of 2 and 4 is 6. And guys, is this not completely amazing that we have been able to build our MCP server, host it on the cloud on Google Cloud, and then basically run this using a client on our laptop. And this is the first step towards basically making MCP servers on the web and make them easily accessible to clients all over. So today we are going to build our own MCP server and we are going to use server sent events or SSE to build it and then deploy it on a URL and use that to connect our client to the SSE server. And we're also going to try and deploy this SSE server over the web to the Google Cloud platform for free. And we're going to try and connect our MCP client to this SSE server remotely. So before we begin, let's understand the basics of what MCP is. Model Context Protocol is a way to allow structured and consistent communication between large language models that are hosted on clients, which we call as MCP clients, and a server, which we call MCP server. There can be multiple servers and the servers can expose functionality like tools, where tools can provide some kind of extra functions that the server can perform for the large language model. Then they can provide data sources. For example, over here we have local data source A, local data source B, or they can provide access to remote services over the internet like we have remote service C over here. Alright, so there are two main components as we just said. One is the MCP client and this is the user facing agent or interface that sends the prompts, receives the responses from the large language model, and handles the user interaction. This also integrates with the server and then sends any kind of requests from the large language model to the server, which then basically responds to your model inputs with actions, tool calls, data, etc. Now there are two ways MCP clients can connect to MCP servers. One is through STDIO, which is standard input output, where each client talks to its own server through standard input output. So there's basically one-to-one connection between the client and the server, and basically the client is given the path to the server file and it starts the server and then starts talking to it. The other way is server sent events or SSE, where multiple clients can basically connect to an already running server using a web-based streaming protocol. So with SSE, you can basically let your MCP clients connect to an already running server using a web link and port, just like connecting to an API. It supports long-lived unidirectional streams of data, perfect for receiving model outputs in real time. On the other hand, STDIO requires a fresh MCP server to be spawned for every single client. That means one server per client. Alright, so let's set up our project directories first. So in your home folder over here, let's make the MCP directory. I already have this made. You can enter this command to make it. Then let's change to the MCP directory and let's make three directories over here, one for all our clients, the other for our servers, and the third for our workspace. So let's make the servers directory and press enter. Then let's make the clients directory and press enter. And then let's make a workspace directory, which we can use for any kind of files that our server creates or any kind of data that it needs to read. This will keep the remaining file systems separate from our workspace, which basically avoids any kind of issues and risks. Okay, now we change to our servers directory and we first check out the code for the server. Please use the link in the description to do a git clone of the server code, and then this will basically make a directory over here which is called terminal_server. I already have done that and I already have this terminal server directory. So this will basically give you the entire code for your server. Let's go to the parent directory and shift to the clients directory now. And then let's clone the GitHub code for our client. Once you do that, you'll have a MCP client directory, which basically has all the code for our client. Alright, so the next thing that we want to do is to install Python. So if you already have Python installed, you can check for the version over here. You can type Python 3-version. And for example, we have 3.9.6, but we need 3.10 or higher. So to install the latest version of Python, we can open a new browser window and say install Python. And let's go to the download Python page over here. Alright, so let's click on download Python 3.13.2 and let's wait for the download to complete. Okay, so once this is completed, you can actually open this and you get an install Python window like this. There's an introduction. Let's click continue. There's a readme over here. So let's click continue over here, and there's a license. I'm going to accept it. I'm going to use the standard installation and not going to customize for now. And let's enter our password. And this is now going to install Python for us. Alright, so we have Python installed now. Let's move the installer to the bin. So this is going to actually open this Python 3.13 folder over here, and it's going to show you all the things that are installed, including the IDLE. Now let's go back to the terminal. Let's type which Python 3, and this shows you that this is installed to user local bin Python 3. So we can now type Python 3 version. And we see that our Python 3 is now 3.13.2. This actually satisfies our version requirement for 3.10 and higher. We're good with this now. Now next we want to install UV, which is a fast package manager for Python that helps us install and run dependencies. So to install that, we're going to paste this command. You can find this in the description. Press enter. So let's wait for some time for this to get installed. Alright, so there's a permission denied error, and you might want to then, and we can see that the error is due to the ownership of local being with root. So the local directory is inside our home directory, so we can actually change the permission over here. So use this command for this, enter your password, and then let's verify if the ownership has been updated.
And yes, we can see that the ownership is now updated over here. So on this permission fail, you might be tempted to run this, with sudo. But running with sudo might install this as root, which could cause permission issues later. So let's not do that, and let's update this permission like this. And let's now try to install UV again and see if it works. Alright, great. So everything's installed. Let's source our environment file so that we can recognize the command UV. And let's type UV dash version, and we can see that UV is now installed. So this is the package manager that we wanted. If you're on a Windows machine, you can actually follow the install instructions on the UV page on GitHub by Astral. And if you scroll down over here, you have the installation over here. So now, why are we using Gemini and not, Anthropic or any other model? Because you can actually go to aistudio.google.com and log in through your Gmail account, and they're going to give you a Gemini API key for free. So there are some terms and conditions that you can check when you take this key, and essentially you can actually use it for free for testing purposes with certain lower limits, and by allowing them to use your data while training their model. And this then makes it an ideal choice for this tutorial and experimentation. So I am on aistudio.google.com, and when I visit this site, it automatically gives me a prompt to get an API key over here. And otherwise, I think there's a button over here also to get the API key. So I'm just going to click on get API key over here. Okay, so there's a code to test the Gemini API, and there's a create API key button over here. So let me just use the API key from here. It's going to now generate the API key for me. And you should use your API keys securely and not share them or embed them in code that the public can view. I'm going to disable this after the tutorial. For now, I'm just going to copy it from here and let it be visible. So to store our API keys securely, what we can do is we can go to the terminal and we can create a .env file. Then let's open that file in Nano. And then let's paste our API key over here. And then before that, we're going to write Gemini underscore API underscore key equal to, and let me add the I over here. And now this is basically an environment variable that I don't need to store in view in my code, and I can use this while developing my MCP client. Let's press Ctrl X and save the file. And what we'll also do is that we'll add this file to gitignore. To do that, write echo.env, which is the file name in double quotes, and then we write it to .gitignore. So this basically prevents accidentally sharing our API key on places like GitHub or any other remote repository.
Alright, so now we have Python and UV both installed, and we also have a Gemini API key from Google, and we have put that in the .venv file in our MCP client directory. Now we need to continue with the remaining setup by creating a virtual environment and installing the requirements. So for that, let's do that first for our client. So let's shift to the MCP clients directory and go to our MCP client. Then we write uvvenv, and this basically creates a virtual environment like we do with python-mvenv. Then we activate this. By typing source.venv/bin/activate. Now we are going to open our PyProjects file, and over here we specify the module that we actually want to build for, which is our client with SSE. We go back to the terminal and we can simply type uv pip install dot to then install all the dependencies. So this has installed all the dependencies that we needed for our client. Please note that you'll already have all these files, and you just need to activate your virtual environment and then install the requirements using uv pip install dot. Alright, so I am back to the home directory. Now let's do the setup for our server code. So we first head over to the server directory. So that directory will be MCP servers terminal server and then SSE server, because this is the directory that actually holds the SSE server code for our terminal server. Just to remind you, the terminal server is a server that can actually run commands using the shell on the terminal of your machine. Now we create a virtual environment by typing uv space venv. Now we activate this virtual environment by typing source.venv/bin/activate. Now we open our PyProjects file over here, and we just make sure that the Py modules is set to terminal_server_SSE. Now we head back to the terminal and we can type uv pip install dot, and this is going to install all the dependencies that we need for our server. Alright, great. So with this, our server and our client dependencies are all installed. We have the code set up and we have everything else that we need to now start testing this. So now let's go through the code for our server first. And you must have checked out the terminal_server code from our GitHub repo. And if you have not, you can do that using the link in the description. And inside that folder, we have an SSE server folder. You might see other files over here, including a Dockerfile, which is basically the simple server that we had made in our previous videos. Now we go to the SSE server folder, and over here we have the terminal_server_sse.py file. This is our main server file, and this is what basically we are going to look through. We also have a Docker file which basically helps us containerize this server, and we'll use this to run our server later on. First, let's look through our terminal server_sse.py file. I have this file open over here, and this basically implements an MCP server using the server sent events or SSE transport protocol. It uses FastMCP. It uses FastMCP framework to expose tools that clients can call over an SSE connection. And SSE allows real-time one-way communication from server to client over HTTP. This server uses Starlette for the web server, Uvicorn as the ASGI server, FastMCP to define the tools, and the SSE server transport to handle the long-lived SSE connections that we are using. And just to explain this briefly, ASGI stands for Async Server Gateway Interface. So it's basically like a middleman that defines how a Python web server like Uvicorn talks to a web app like Starlette. It allows async input-output, so your app can handle thousands of users, use WebSockets, and stream data like SSE. So this is what ASGI does. Uvicorn is the ASGI web server. It's the actual engine that runs your Python app. It listens for HTTP requests, understands the ASGI protocol, and passes incoming requests to your app, which is Starlette or FastMCP. It basically brings incoming data to your app and it sends back the responses to the browser. Starlette over here is the lightweight web framework. So it's a minimal ASGI web framework, and we use it to define the routes inside our app like /SSE and /messages that we are going to look at below. We use it to define the request handling logic as well, and the middleware background tasks, etc. So this is the web framework that we are using. And all this connects to MCP, which is basically the language model communication protocol. The MCP over here defines how the clients talk to the server, what tools are available, how to send, receive structured prompts, responses, tool calls, etc. And finally, we have SSE or server sent events. And this is basically a streaming HTTP protocol. It's a one-way communication, server to client, and it's used for pushing updates, tokens, results in real time, and it's perfect for AI and model outputs. In this case, we are using it for connecting the MCP client to our MCP server over HTTP and allowing the server to stream back results from the tool calls. So we basically have an MCP client/agent in the browser which connects via SSE over HTTP to our server, which is the Uvicorn server. And this uses the ASGI protocol bridge to connect to our Starlette web app. The Starlette web app handles all the logic, routes, etc. and basically connects with the MCP server that offers the MCP tools like run command and add numbers, which we're going to look at below. So this is basically the visual representation of how our flow is going through. And now we'll go through the code. So we import our basic libraries and all the MCP libraries. So we have the core MCP wrapper to define tools and expose them. We have the underlying server abstraction used by FastMCP, and we have the SSE transport layer. We then import everything related to Starlette. So we basically import the web framework to define routes, import routing for HTTP and message endpoints through route and mount, and we import the HTTP request objects through request. Then we import Uvicorn, which is the ASGI server to run the Starlette app. And then we start with step 1, which is basically initializing FastMCP instance. And this is basically our tool server. So we call this terminal, and this is our MCP server. We define the workspace as the home directory /mcp/workspace, which we've already defined in the previous steps. We then define our first tool, which is the run command tool. And the purpose of this tool is to execute a shell command on the terminal in our local machine and return the output. We use the mcp.tool decorator to mark it as an MCP tool, and it's basically an async function that takes in a string, which is the command that we need to run on the terminal, and then responds with a string output, which is the output of the command or an error as the case might be. And this function is pretty simple. So we use subprocess to run this on the shell, and we return the std out or std error, whatever the case might be. If there's an exception, we basically catch it and return the exception string over here. We then have the second tool, which is add numbers, and it's also a simple tool to add two numbers and return the result. So we again have the decorator to mark it as an MCP tool, and then this tool takes in two arguments, A and B, which is the first and the second number, and it adds the two numbers and returns the sum, which is a float value, which is the sum of A and B. And that's a very simple tool over there. Now we need to create the Starlette app to expose the tools via HTTP using SSE. So we basically define this function called create Starlette app. This basically constructs a Starlette app with SSE and message endpoints. MCP server is the core MCP server instance, and we enable debug mode for verbose logs. The full Starlette app with all the roots. Alright, so then we create an SSE transport handler to manage the SSE connections. After that, we define a handle underscore SSE function, which basically is triggered whenever a client connects to /SSE. So this is the route that the client will connect to, and it will trigger this function. And what this does is basically it handles the new SSE client connection and links it to the MCP server. So how do we do that? We open an SSE connection and then hand off the read and write streams to MCP. And then we return the Starlette app with the configured endpoints. So we have two endpoints. One is the /SSE, which is for initiating the SSE connection. And then we have the messages endpoint, which is basically for post-based communication, which basically is used when we create the SSE transport handler over here. Now we basically start the server using Uvicorn. So we first get the underlying MCP server instance from FastMCP into MCP server. We import argparse, which is basically for passing command line arguments for host/port control. So we create a parser with a description. We then add the host and the port over here. We are using localhost and we are using 8081 as the port. And then we basically get the arguments from the parser. We built the Starlette app using the create Starlette app function that we basically used earlier, providing it the MCP server. And we have the Starlette app over here. And then we launch the server using Uvicorn by saying uvicorn.run, and we provide the app with the host and the port using the arguments that we just passed above. So in essence, if we go back to our visual representation, we have created a Starlette app, which when receives a connection over /SSE, hands it off to the FastMCP server, which exposes the tools like add numbers and run command. The Starlette app also provides another route, which is /messages, which is for post initialization communication. And the Uvicorn server basically runs this app using the ASDI protocol bridge. So this was a quick overview of the code, but for now we are going to head over to our client code to just have a quick walkthrough of that before we start testing our client and server together. Alright, so this is the client _sse.py file, and this implements the MCP client that connects to an MCP server using server sent events or SSE transport. This client builds up upon the previous client that we built, which is client.py, that uses STDIO, and the only difference between the two clients is the difference between STDIO versus SSE being used for communication. So let's go through the code for the client. So we first have some basic imports over here, which are self-explanatory. You can actually read the comments over here to understand what these are being imported for. Then we import the client session from the MCP package, and this basically manages all the communication with the MCP server. We then import the SSE client helper. We then import the components from the Gemini SDK for AI-based function calling and large language model integration. So over here, we are basically importing the main Gemini SDK module, GenAI. This we'll use to configure the Gemini client and send prompts and get completions. So this is the core SDK entry point. Then we import the types. The types module contains important data structures used for tool and function declarations, generation configuration, and structured prompts and response handling. Then we import from types the tool and function declaration. So this basically imports the specific classes which is used for function calling. The tool represents a tool that can be invoked by the AI model. Each tool tells the model what it can do, how to call the function, and what parameters are expected. The function declaration defines an individual function's name, description, and parameters. So we're going to use this below in the code. Generate content config is used to configure how the model generates content. So we basically set the temperature and other details over here, and again we're going to use this when we go down in the code. We then import the .env file to load environment variables, and over here we're basically storing the Gemini API key. This is a good practice to not expose your API key while you're actually using it in the code or you're pushing it to a Git repository. If you remember, we have added the .env file to gitignore. We then actually load the file after importing the required packages. We then have our main MCP client class with the initialization function that initializes the MCP client. So this constructor is basically going to set up the Gemini AI client using the API key from the environment variables, and it's basically setting up the placeholders for the client session and the stream context, which is going to manage the SSE connection. The Gemini client will basically be used to generate content and request any kind of tool calls from MCP server. This is a placeholder for the MCP session that manages the communication with the MCP server. These will basically hold our context managers for the SSE connection. So there will be a SSE stream lifecycle that we need to manage the context for, which will be held over here. And there will be an MCP session lifecycle, which will be held over here. Now we use the os.getEnv function to actually get the Gemini API key. In case we don't find it, we raise a value error. And finally, we initialize the Gemini client with the API key, and this client is basically used for the communication. So next in the MCP class, we have the connect to SSE server function. Now, if you are following this channel from before, you know that we actually made a client with a connection function that uses STDIO. And this is the difference between that client and this client, that we are actually using SSE transport to connect to the MCP server. So the steps that we perform are we open a SSE connection using the provided server URL. So this is the server URL that we're going to use. We use the connection streams to create an MCP client session. We initialize the MCP session, which sets up the protocol for communication, and we retrieve and display the list of available tools from the MCP server. Alright, so we first open the SSE connection using the SSE client, and we store it in the streams context variable that we defined above. So the SSE client function is returning an async context manager that yields the stream or the data channels for communication, and this is what we are going to store in the streams context. So we now get that data channel or streams using the streams context from above by entering the async context. So streams is expected to be like a tuple, like reader and writer, that the client session can use. Now we create an MCP client session over here using the streams provided by the SSE connection. So we have the read and write streams. We use that to now create the MCP client session, and the client session object basically handles sending and receiving messages following the MCP protocol. Again, we get the session context first, and then we enter this session context to create the client session. Now we initialize the MCP session by calling session.initializes, and this basically sends an initialization message to the server to negotiate capabilities and start the protocol. Alright, so now we are going to finally retrieve and list the available tools from the MCP server, and we basically print for the user that we are initialized the SSE client and we are listing the tools, and then we call session.listTools, and when we get the response, we get the list of tools from the response as response.tools, and then we basically say we are connected to the server with tools, and we print the tool name for each of the tools in the tools list. Alright, so then we have a function which basically converts MCP tools to Gemini format. So the tools that we get from MCP have some fields or properties which Gemini does not expect, and we need to remove them. So we basically have a convert MCP tools to Gemini function. Let's have a quick look at this to understand what it does. So this is the convert MCP tools to Gemini function, and I'm going to just scroll down to show you exactly what it's doing. So it basically creates an empty list of tools, and for each tool in the MCP tools that it has received as an argument, it's basically going to clean the schema for the parameters. And what cleaning is done is inside the clean schema function. And if you look at the clean schema function, it is basically just removing the title key if it exists inside that schema recursively throughout all the properties. And that's it. That's a simple removal that we need to do because Gemini does not expect this title key if it exists in the schema. And now going back to the convert MCP tools to Gemini function, after we have cleaned the schema, we just create a function declaration. That is how Gemini wants the function declaration to be. And if you remember, we imported this from the Google Gen AI SDK types. This is the type it expects for how to define a function, and we provide the name, which is the tool.name, and the description and the parameters which have been cleaned to remove the title. Now we wrap the function declaration into a tool and we assign it to a Gemini tool object, and then we append this to the list of Gemini tools that we have and return this Gemini tools list from here. So this is all that the convert MCP tools to Gemini does. You can have a look at the function. It's pretty self-explanatory based on all the comments that I have put over here. So we now get all the function declarations for the MCP client, and this basically completes the connect to SSE server function. Next we have the cleanup function. So it basically cleans up the resources by properly closing the SSE session and stream contexts. So we basically need to manually call their exit functions, and this ensures that all network connections and resources are gracefully closed when the client finishes. And that's what we do over here. Now we have the process query function, and this is a major function that does a lot of work for us to process the query given by the user. So it basically uses the Gemini API to process the query, and the Gemini API might request a tool call via function calling, and if that happens, then the response is passed and the MCP server is invoked to call the tool. The result from the tool call is then sent back to Gemini for a final response. The steps that we follow are: we format the user's query as a structured content object. We send the query to Gemini including the available MCP tool declarations, and if Gemini's response contains a function call request, we execute the tool on the server, and then we send the response from the tool execution back to Gemini. If Gemini's response contains a function call, we send the result of the tool execution back to Gemini, and then we get a final response which is processed as text from Gemini. And then we basically get the final response from Gemini and return that. The arguments are just the query string, and that final response string is then returned as the return value. All right, so let's go through the code now. So we create a Gemini content object. It represents the user's query, and this basically includes a role which is user, which basically says that this is coming from the user, and the query is text wrapped in a part. The role and parts are provided to the content class, and this is basically then used to form the user prompt content. Then we send the query to the Gemini model. So we basically use generate content to do that. We specify the model, we specify the contents, which is just the user prompt content over here, and we basically generate the content configuration which we imported above. Over there we provide the tools, which is based on the function declarations that we basically got from converting the MCP tools to Gemini tool definition formats. So we get the response over here, and then we basically parse the response. Before that, we basically create an empty final text list to accumulate the final response text. Now for the response, we look at each candidate in response.candidates, and then each candidate has content parts, and we look for each part. And if the part is basically a function call, we extract the name of the tool and the arguments, and we then tell the user that Gemini has requested a call to this particular tool with these particular arguments. And finally, we attempt to call the specified tool on the MCP server, and here we basically use the MCP session to call the tool with the name and the arguments. We get the result, and this result is then put in function response, or if there's an exception, we put the exception string inside the function response, and then we create a function response part where the response is the function response that we defined above, and we name it as the tool name. And this is basically the function response part. Then we wrap the function response part in a content object marked as coming from a tool. So the role is basically specified as tool. And then we again call the Gemini API using generate content. We specify the model over here, and in the contents, we now include all the three parts. So we have the initial user query, we have the tool call that was requested, and we have the response from the tool call. All three are included so that Gemini has the full context of what's happened. And we give the function declarations again for continued use. Based on the response that we get, we basically again look at candidates, content, parts, and text, and we append that text to the final text over here. In case there's no function call that was required, we basically just use the text provided by Gemini and append it to the final text over here, and we return this final text over here. So this basically is the process query function. Next, we have the chat loop. So chat loop is basically an interactive chat loop that runs in the terminal, and it basically waits for the user input query. It prompts the user for the query. If the user type quits, then it basically breaks out of the loop. Otherwise, it uses the process query function to process the query provided by the user and awaits the response, and then prints the response over here. Finally, we have the clean schema helper function that we've already looked at, along with the convert MCP tools to Gemini function, which we also had a look at earlier. The last but not the least is the main function, which is the main entry point for the client. And this basically checks if, so this is basically invoked when we run the client Python script, and this basically checks that the server URL is provided. It creates an instance of the MCP client over here. Then it basically tries to connect to the SSE server using the connect to SSE server function, and then it basically calls the client chat loop and prompts the user for a query. And finally, it basically does all the cleanup that is required before exiting. And over here, we simply run this main function using the async IO event loop by using async IO.run and passing the main function over there. So that's all for your client underscore SSE.py function, and this is our SSE-based client. So let's also look at the Docker file that we are going to use for our terminal server. It's a simple Docker file, and we basically use from Python 3.11 Slim, which is the official Python 3.11 Slim image, as the base image. We set the working directory inside the container to /app. We copy all the files from the current directory in the local host basically to the app directory in the container. Then we install the required Python packages from requirements.txt. We expose the port 8081 so that the container can accept incoming connection. So basically 8081 is the port where we'll be able to access the MCP SSE server. And then finally we use the Python command to run our SSE server, which is the terminal underscore SSE.py file. So that's all for the Docker file. It's a pretty simple Docker file to actually run this server. All right, so now let's go ahead and run our server first. So we can click here to open the terminal. So let's use the docker build command, docker build -t to tag the image, and let's name the image terminal underscore server underscore SSE, and let's not forget to put the dot for the build context and press enter. This is going to build our docker image with all the requirements, etc. And now this image is actually built. Now let's run our server. Now let's run the container using docker run. The --rm is going to help us clean up when the container exits. The -p helps us match the local port to the container port. The -v is a volume mount, and we are basically mounting the localhost volume located at our workspace to root/mcp/workspace inside the container. And then we provide the name of our image and we press enter. And now we have our server running at localhost 8081. Now let's run the client. So we're going to click over here to open the terminal, and we are going to use the command uvrun. So we'll use uvrun client_sse.py, which is a client file, and we are going to provide the URL for our server as localhost:8081 with the port /SSE, because that's the place where our server listens for initialization. Let's press enter. And now it says initialized SSE client listing tools, and now it's connected to the server with tools run command and add numbers. So let's test this out. So let's ask Gemini to actually add 2 numbers. So I'm going to say add 2 numbers, 2 and 5, using the tools, please, because it's a simple operation. It might just add it on its own. I wanted to use the tool and check if the server is running over that SSE connection or not. So let's press enter. All right, so now we get the result that Gemini requested a tool call, add numbers with arguments a equal to 2 and b equal to 5, and the sum of 2 and 5 is 7.0. So that's wonderful. Our server is now running over a HTTP connection, and now we can actually go and deploy this server on the Google Cloud platform and try to use this over a remote connection, because this is still on our local machine on localhost. So I'm going to deploy this server on the web. Let's try to do that now. Alright guys, so now we are going to deploy our server to Google's cloud using Cloud Run. And there's a video for this that you can actually look at to set up Google Cloud and a Google Cloud project using your Gmail account. And for a new project, you can actually get $300 in free credit. So you actually don't need to spend a dime to actually set it up and deploy your MCP server to the Google Cloud. I'll give the link for the video in the description and the pinned comment. To deploy our MCP server to Google's cloud, we need to first build the Docker image for that for Google Cloud. So let's change to the terminal server directory. Alright, so I'm going to change to MCP server's terminal server SSE server directory. Then I'm going to use a docker build command. I'll specify the platform as Linux/AMD64, which is needed for Google's cloud. And I'm going to tag this as per Google's cloud naming conventions, which is gcr.io for Google's container registry. Then we have the AI language -prod, which is my project name. And then we have the name of the image and the dot for the build context. Let's press enter. Alright, so once the build is done, we can actually push the image to Google's container registry, from where we will be able to actually deploy it to Google Cloud Run. To push the image, we are going to use docker push gcr.io / the AI language prod / the MCP SSE server, and this is going to push the image that we just created. Alright, so once the push command is completed, we'll actually run the deploy command. This is gcloud run deploy. We provide the name, which is MCP SSE server. Then we provide the image tag. We basically use the managed platform. We choose a region and we provide a port, and we allow unauthenticated access for this demo. Be sure that you actually deactivate the Cloud Run API after you have tested it yourself, and use some kind of security mechanism on this, as leaving it unauthenticated might be risky. Let's press enter to deploy it. Alright, so this deploys and provides us a URL for the service. Now let's clear this and move to our client directory. Now we'll write uv run and then we'll write the name of our client and we'll provide the URL that we just got and we'll put SSE as the endpoint because that's needed for initialization. Now let's press enter. And guys, is this not amazing that now we have our MCP server running on Google's cloud over here and we are able to run our client with that particular endpoint. So now we get initialized SSE client listing tools and is connected to server with tools run command and add numbers. MCP client has been started, type quit to exit. So let's type our query. So we are going to use the add numbers tool and I'm going to ask it to add two numbers. Now I've asked it to add 2 and 4 using the add numbers tool. Since it's an easy operation, I specifically mentioned the tool to be used because I want Gemini to use the tool rather than just adding the numbers itself. And now we'll check whether our MCP server hosted on the cloud can actually connect with the client that's running on our laptop right now. Let's press enter and see what happens. Okay, so Gemini requested tool call add numbers with arguments 4 and 2. That's perfect. And then the sum of 2 and 4 is 6. And guys, is this not completely amazing that we have been able to build our MCP server, host it on the cloud on Google Cloud, and then basically run this using a client on our laptop. And this is the first step towards basically making MCP servers on the web and make them easily accessible to clients all over. Thank you very much for watching. If you like this, please do give this video a like and subscribe to my channel, and I'll see you in the next video.